Okay, so convergent and divergent series. Now, the first example that we did, we worked out an example with a convergent series. Let me see if I can pull that one up. All right. Yeah, this was the last example that we did. Right. So for this one, right, we were able to show that we could create partial sums out of this series, right? And the nth partial sum was provided, right? 2 to the power of n minus 1 divided by 2 to the power of n. And what we had to do was determine whether this series converges or not. And the idea was that if the limit of the partial sums exists, then the series converges. But if it doesn't exist, then the series diverges, right?
Yeah.
So what we did was we took the partial sum, right? So we took that partial sum, 2 power n minus 1 over 2 power n. We took the limit as n goes to infinity, and that turned out to be 1, which is equal to s, capital S, right? So our capital S, which means the full sum of that series, is equal to 1. Therefore, it converges to 1. So this is an example of a type of series called a telescoping series. All right, so in this example, we have we have the sum from n is equal to 1 to infinity of 1 divided by n minus 1 over n plus 1. Right, and what we want to do is we want to determine whether or not this series converges. Right. So naturally, when you have these kinds of series, you want to sort of write out the first few terms to see if you can spot out some kind of pattern, right? And then you can maybe use that pattern to create a formula for the nth partial sum, right? So let's expand the series. And write the first few terms. All right, so what we're going to do is we're going to write the first few terms here. We're going to say the sum from n is equal to 1 to infinity of 1 over n minus 1 over n plus 1 is equal to, well, when n is equal to 1, you end up getting 1 minus a half. All right, this is when n is equal to 1, right? We have 1 over here minus 1 over 2. And we get this term. And then when n is equal to 2, we got 1 over 2 minus 1 over 3. When n is equal to 3, we have 1 over 3 minus 1 over 4. Right, and so on and so forth. So if you take a close look at this series, right, you see that the minus 1/2 over here cancels out with the positive 1/2 over here, right?
Yeah.
And then the minus 1/3 over here cancels with the positive 1/3 over here.
leaving 1 and negative 1/4.
Yeah. Right. So this cancels with this. This cancels with this, and this cancels with this, right? So it looks like you're only gonna have 1 remaining,
Yeah.
and then
'Cause
you're
the one-
always.
The 1/4 would continue, like it would just keep canceling, right?
Yeah, it would keep canceling.
Okay.
But say for example, you reached the nth term, right? Because this was term number 1, right? N equals 1, n equals 2, and n is equal to 3, right? So say for example, for your partial sum, you're only concerned with when n is up to equaling to 3, right? When you get to n is equal to 3, all you have left is 1 minus 1 over 4, right?
Yeah.
So this just so happens to be negative 1 over n plus 1 because n was 3, right?
Yeah.
So you have 3 plus 1 down here, which gives you 4. So you have negative 1 over 4. So for the nth partial sum, whatever the value of n happens to be, you're going to end up with 1 minus 1 over n plus 1. Right? So I'll say that one more time. When you get up to some particular value for n, say for example n is equal to 3, all the other numbers have canceled out until that last value, right? In our case, that last value happens to be minus 1 over 4. But if you look at the denominator, the 4, right? 4 is just n plus 1, right? So n equals 3 plus 1. So the expression that we can write to identify the nth partial sum happens to be 1 minus 1 over n plus 1, whatever the n value has to be. So we can say cancel all equal terms, or we'll say, cancel all values of opposite sign and leave the remaining term for the nth term. We could say leave the remaining numbers for the nth term. Right. So you can use the remaining values to create an nth partial sum. Right, so these partial sums are not always going to look, they're not going to have the same patterns. But the idea is that you're combining terms that cancel out and make 0 and leaving the remaining terms, right? And then you're rewriting those remaining terms using a general formula, right? And that formula is the nth partial sum. So in our case, our nth partial sum comes out to be S sub n is equal to 1 minus 1 over n plus 1, right? And then you can see that for the case when n is equal to 3, we end up with the first 3 terms that we wrote out here. So it works for n equals 4, n equals 5, and so on. Okay, so let's say this example is called a telescoping series. Okay, so now that we have the partial sum, right, we can take the limit just like we always do, and see if this limit converges or diverges. Okay, so take the limit to determine convergence. So yeah, these telescoping series can really be kind of a headache to come up with a partial sum formula, because they're not always, very obvious to spot out. It's like you have to see a pattern, and sometimes you need to write a whole bunch of terms, maybe like 5 or 6 terms, before you see the pattern emerge, and you can say, oh,
Yeah.
that's it, right? This one we only needed to do like 3 terms.
So, what other patterns emerge besides canceling out? Would are other patterns let's say even numbers or odd numbers?
Yeah.
Or
Yeah.
okay.
Because you can end up with patterns between even and odd numbers that cancel out, right? Something's always going to be canceling out, right? But it's just going to be different, right? So you might have like square terms, like even powers that cancel out, and then the odd powers stay, right? So it's sort of kind of like, again, just pattern recognition for you to look at the series, look at the first 4 or 5 terms, maybe 6 or 7, and then you'll see what cancels and what stays. And then the remaining terms, you use that to create the nth partial sum. So let's take a look at, right, now we want to take the limit, right? So let's take the limit and see what we get here. Right, so we're going to take the limit as n goes to infinity of 1 minus 1 over n plus 1. And this is a fairly straightforward limit, right? The n goes to infinity, which means your second term here goes to 0. So you're just left with 1. Right, so that means that your original series converges, and it converges to 1. So here's some interesting things that you might want to keep in mind for telescoping series, since they're going to show up a couple more times.
Okay.
Right, so if you noticed, right, with the series that we wrote over here, right, all of the intermediate values canceled out, right, except for the very first value and then the very last one, right? So for a telescoping series, right, so we'll say a telescoping series will converge if and only if B sub n approaches a finite number as n approaches infinity, where we can say so where s of n is equal to b1 minus b sub n plus 1. Right? And the telescoping series that we did in this problem, right? Because I remember you asked me, what other kinds of patterns will we see? Well, we always see patterns of this form, right? Well, we may have different patterns, but for this particular problem, the pattern that we saw was the first two terms was a difference, right? So like b1 minus b2 and then plus b2 minus b3. You may have other patterns, right? Maybe b1 minus b2 plus b3 minus b2. It comes in different forms, but you're always canceling something out, right? So we'll say in the previous example, our telescoping series was of the form b1 minus b2 plus b2 minus b3 plus b3 minus b4 plus ... right? So we were able to see that the b2 would cancel out, b3 would cancel out, right? And after only the first three terms, we noticed that b1 remained, and then the last part of the nth term also remained. All right, so let's do one more example with the telescoping series, and you'll see, another kind of pattern that can emerge. All right, so for this one, we want to find the sum from n is equal to 1 to infinity of 2 divided by 4n squared minus 1. Right, we want to see if this series converges or diverges. If it converges, then what does it converge to? Okay. Now, for this series, if you notice, right, the denominator is a difference of perfect squares. Right, we got a 4n squared, which can be written as 2n quantity squared, right, and then minus 1. So we can actually break this up into two factors, and then we can use partial fractions to separate it into two terms, just like the way we had two terms over here. Right, so we're going to say factor denominator, factor the denominator, then apply partial fractions to rewrite the series as a telescoping series. All right, so let's do that. So we got 2 over 4n squared minus 1. Right, which we can factor into 2 over 2n minus 1 times 2n plus 1. And if we apply partial fractions, we can break this up into 1 over 2n minus 1. Minus 1 over 2n plus 1. Right? So from this step to this step, right, it's just applying partial fractions, where basically we write the fraction as a over the first denominator plus b over the second denominator, right? Then we solve for the constants a and b. So if you actually work it out, you end up getting a equals 1 and b equals negative 1. So your partial fractions gives you the two fractions 1 over 2n minus 1 minus 1 over 2n plus 1. So this is now a telescoping series because you're summing the difference between two terms, right?
Okay.
So let's write out the first few terms and see if we can spot out another pattern. All right, so let's start with n equals 1. All right, when n is equal to 1, we have 1 over 2 minus 1, which is just 1 over 1. And over here, we get minus 1 over 2 plus 1, so that's minus a third. And for the next one, if n is equal to 2, we get 1 over 3 minus 1 over 5. Okay, so for when n is equal to 3, we get 1 over 5 minus 1 over 7. Right, and so on and so forth. Alright, so let's choose, out of the first few terms that we wrote, let's just choose an arbitrary nth value, right? So we're going to say, suppose we want the partial sum for when n is equal to 3. Right, so we got when n equals 1 over here, n equals 2 over here, and n equals 3 over here. Right, so we see that for n equals 1, the minus a third cancels out with the plus a third for when n is 2. So minus a third and positive a third cancel. Minus a fifth, positive a fifth cancels. So we end up with, for our n equals 3, we end up only with the first value from the first term, the 1, right, minus 1 over 7, right? So the 7 is just 2 times the 3 plus 1, right? So it's like doing 1 over 2n plus 1, right? So it looks like for our nth partial fraction, whatever n value we may choose, it's going to turn out to be 1 minus 1 over 2 times that n value plus 1, right? So we can say our s sub n is equal to 1 minus 1 divided by 2 times n plus 1. Alright, so now that we have the nth partial fraction, or the nth partial sum, we can just take the limit as n goes to infinity and see if that converges or diverges. Alright, so let's do that. We're going to take the limit as n goes to infinity. Of 1 minus 1 over 2n plus 1. Alright, so again, this is just another very straightforward limit. And the second term goes to 0 again. So we just end up with limit equals 1, which means that the sum of this series is also equal to 1. So we're going to say this also converges.
So for the patterns, at least in the explanation above, it's talking about how the pattern's kind of like a B in one parentheses and a B of the same
Right.
likeness in a different parentheses. So they're almost like side by side.
Exactly. Yeah, exactly. So it's easy to spot out which ones cancel. But like I said, I've worked on some telescoping series where you don't see what cancels until like maybe 2 terms down the line. So these are very straightforward where they're next to each other, so it's easy to see what cancels. And then you can just say, okay, this is what it looks like. Right, and as for the limits that you have to take, the limits are also pretty straightforward because one term vanishes to 0, right, leaving the other constant alone. So it's easy to see what your limit turns out to be. And also when it converges, right, whatever it converges to, whatever your partial sum converges to, that's what the sum of that infinite series is.
Okay.
All right, cool. So let's move on to another type of series called geometric series. Okay, so geometric series are a lot easier and more straightforward to handle than telescoping series because the rule is very simple. Right? It's a very straightforward rule to identify. You're just looking for a series where every term is the same ratio from the previous term. All right, so let's look into this. All right, so a geometric series, start by saying that a geometric series is a series of the form, and you know what? I'll just take a screenshot of what it looks like. But it's just a series where you have a common ratio between each of the terms. So yeah, your geometric series is a series where you have the summation from n equals 0. So n starts from 0. Right, to infinity. Right, and it's of the form a times r to the power of n. So a is called your, well, it's typically called your first term. Right, this is your first term. And then your r to the power of n is the common ratio. All right. So for example, say your common ratio is 2. And let's say your first term was 1, right? So you would have 1 plus 1 times 2 plus 1 times 2 squared, all the way to 1 times 2 to the power of n.
Okay, so in a way, I'm kind of confused, like what the ratio is. Well, I know R is supposed to be the common ratio, but like I was thinking, like ratio between two terms, we'd see like a fraction of some sort.
Yeah, but if you think about it, say for example you take this term here and the previous term here, right?
Yeah.
If you did AR squared, which is this term, divided by AR, you would get R, right?
Yeah.
Right, so R is the common ratio between each successive term, right? So
Okay.
if you take one term and take the ratio of that to its previous term, you would always get R.
Okay.
So let me show you an example. So we'll have sum from n is equal to 0 to infinity of 2 times 1 over 3 to the power of n, right? So when n is equal to 0, we just get 2. When n is equal to 1, we get 2 over 3. When n is equal to 2, we get 2 over 9. 3, we get 2 over 27, and so on, right? So if we take the ratio of any term to its successor, or not its successor, but to its predecessor, we find that the ratio is the same 1/3. Okay, so for example, if we do 2 over 9 to 2 over 3, so 2 over 9 to 2 over 3, well, that just gives us 2 over 9 multiplied by 3 over 2, which comes out to be 1 over 3. All right, so this is our common ratio. Make sense?
Yeah.
All right, cool. So that's how you can tell, right? whenever you have a series, if they have a common ratio between each term, right, then you know that that's a geometric series.
Okay.
Okay, let me show you. Well, let me write the convergence theorem for a geometric series. So say convergence of a geometric series. Okay, so we'll say a geometric series with ratio r So a geometric series with common ratio r diverges when the absolute value of r is greater than or equal to 1. Okay. So if the absolute value of r is less than 1, then the series converges to the sum So it converges to this sum here. Sum from n is equal to 0 to infinity of a times r to the power of n equals a over 1 minus r. Right, when r, absolute value of r is less than 1. Alright, so if your series is a geometric series, then it if it's a geometric series, then it converges if the magnitude of r is less than 1. Okay, so far we've talked about two kinds of series. Right? We've talked about the telescoping series, and we've talked about the geometric series. Right? So when you're looking at a series, you're trying to determine what category it falls into. Is it geometric? Is it a telescoping series? Or is it something else? Right. All right, let's look at an example. So we'll say determine the convergence or divergence of the following geometric series. so let's start with our first series. We'll do the sum from n is equal to 0 to infinity of 3 over 2 to the power of n. Right, so sum from n is equal to 0 to infinity of 3 over 2 to the power of n. Okay, so sometimes your geometric series might not be written, obviously. It might not be made obvious, right? So it's up to you to sort of like, if you suspect that the series might be a geometric series, right, see if you can simplify it and rewrite it so that it fits this form. And if you can do that, okay, this is a geometric series. Now I just need to check if the common ratio is less than 1, if the magnitude of the common ratio is less than 1, and if it is, then I know it converges. Okay, so yeah, let's try this one out. So you see this one, it's not written in that AR power n form, but we can make it look like it, right? All we have to do is separate the 3 and the 1 over 2n, and then it'll look more like it. All right, so we have the sum from n is equal to 0 to infinity, right? So the 3 over 2 to the power of n, we can write it as 3 multiplied by 1 over 2 to the power of n. All right, same thing.
Did we factor out the 3 to get that, or?
Yeah, I just factored the 3 out, and then for the 2 to the power of n, since it was underneath a 1, right, we can just write the whole thing as 1 over 2 power of n. Right? So we factored the 3, the 1/2 we wrote it as a power of n, and now we can, if you like, you can also write out maybe the first 2 or 3 terms, right? So we get 3 times, for n equals 0 is just 3 times 1, right? And for n equals 1 is 3 times 1 over 2, then 3 times 1 over 4, and so on. Okay, so what's our common ratio here?
2 and 4, and I guess 3? Or is this supposed to be 1?
I want you to take a quick look at that.
Yeah.
Right. Start from here, the example we did here, how we determined what the common ratio was, and then apply it to this one here.
Okay. Okay, so in the last one, we were trying to find the ratio that was the same as like 1/3 there. Well, 1/3 was our common ratio, so
Right.
we got that because the setup is like A is your first term and your
Right.
R is your common ratio.
There
So
you
in our
go.
current problem, our 1/2 is our common term.
Yep. Right. So our common ratio is 1 over 2, right?
Yeah.
So we can say common ratio is 1/2. Okay, so now we know what the common ratio is. What's our first term?
Term is 3.
All right, so the first term is 3. All right. Now, the next question is the absolute value of the common ratio, is it bigger than 1 or less than 1?
It's less than 1.
Less than 1, right? So we know that the absolute value of r is absolute value 1/2, and that's less than 1, right? All right, so now, according to our convergence and theorem for geometric ratios, if absolute value of r is less than 1, then the series does what?
The series converges.
Right. So in our case, it's less than 1, so we can conclude that the series converges. Okay. Now the next question is, what does it converge to?
Okay. So, in the previous one, common ratio is the same as 3.
Right. So I want you to look here.
Yeah.
Right. What does it converge to?
I was going to say our n.
Say that again.
N.
What does it converge to?
It converges to the sum. So not the n, but the ar to the power of n.
No.
That's supposed to be the sum, right? Or
That's the sum. And what is that?
Yeah.
Right. It converges to this.
Yeah.
Right? It converges to the sum. This equals this.
Okay.
So we know our leading term. We know our common ratio, which means we can calculate what this series converges to. Right? So now we can say, okay, so we know it converges. So we know that the sum is equal to a over 1 minus r. Our a is 3. Our r is 1/2. So now we simplify it. 3 over 1/2. So it converges to 6. All right. So we get the common ratio. All right, we have our common ratio. We get what the first term is. We determine if the series converges. Okay, it does. So what does it converge to? So it converges to this formula. 3 over 1 minus 1 over 2 gives us 3 over 1 over 2 gives us 6.
Okay. So okay. So from the beginning, we're trying to determine the convergence or divergence of the following geometric. So, why do we have to figure out where it converges to if the question is just asking whether diverges or converges.
Yeah, I just put that in there just so we can practice this, because normally with geometric
Okay.
series, if it does converge, they always ask you what it converges to.
Okay. So from the beginning,
Hmm.
we have like what they give us, which is just the 3 over 2n. So I'm guessing we have to convert that into an AR to the power of n in order to get
Yeah,
our first term in our common ratio.
right,
Okay.
right.
So from there, then on, we create our series, which is just the A, then the AR, then the AR squared, and then so
Right,
on to like the ARN.
right.
Um, with that, we're able to find our common term, our first term, and our absolute value of R,
Right.
which tell us whether the series converges or not.
Hmm.
So if it didn't converge, we don't have to do that second part of it where we
Yeah,
find the number 6.
right.
Okay.
So if it doesn't converge, then yeah, we wouldn't have to do this, because that just means that it goes to plus or minus infinity.
Cool.
All right, cool. So I just want you to be aware of a pitfall, and that pitfall is that make sure that when you're dealing with the series, right, it's numbers that you're dealing with in here. So, like, for example, let's say you had a series from n is equal to 0 to infinity, and it was 4 times 2 over n power of n. This is not a geometric series because there's an n inside of the parentheses,
Okay.
right? So it's not going to be a common ratio because every term is going to have a new value of n under here. So this is not a geometric series. Right? So warning over here, because it's a common mistake. It looks like a geometric series, but it's really not. Okay, so that's good. Let's try out one more example, and then we'll move on to the next thing. Yeah, let's try this one.
Oh,
Mm-hmm.
oh, okay. Yeah, my AirPods died and it muted me.
Okay, so for this example, let's see. There's one more over here. So again, you have to determine whether or not it converges, and then state what it converges to. All right, so this one is the sum from n is equal to 0 to infinity of 3 over 2 to the power of n.
So our first term would be 3. Our common ratio would be 1/2.
Okay, so I want you to take a closer look at it because our first term is not 3,
Okay.
right? if you try to separate the 3 from the 2, you're going to end up with 3 to the power of n times 1 over 2 to the power of n. Because the 3 is inside the parentheses, so it's also being raised to the power of n.
Yeah. Okay.
So the first term is not 3.
Can we turn it into like a multiple of some sort? So like have a negative n, like a negative power?
No, not exactly.
Okay.
Right? So in this example, right, remember the common ratio is the number that's being raised to the power of n, right?
Yeah.
So that means our common ratio here is 3 over 2, because we have 3 over 2 to the power of n, which means the leading value, the leading term, has to be 1. Right? So you can write this as 1 times 3 over 2 to the power of n.
I was thinking that too, but I wasn't sure. So like, I wasn't sure if like 1 would exactly be there.
No,
You know?
yeah.
Okay.
Yeah. So if you have a variable x, it's the same thing as 1 times x. You just don't need to write the 1.
Okay.
Right? So just like this one, 3 over 2 power of n is the same thing as 1 times 3 over 2 to the power of n. So,
Okay.
right, and also the leading term, you can also get it just by calculating what the first term is. If you set n equals 0, right, what's the first value that you get? You get 1, right?
Yeah.
Yeah, so if we plug in maybe a couple of values for n, when n is 0, we get 1. When n is 1, we get 3 over 2. When n is 2, we get 9 over 4, right?
Yeah.
Right, so whenever, let's say you're not sure if it looks kind of complicated, just plug in maybe 3 terms, right? And then from those 3 terms, you can tell what your leading term is should be. And then use maybe the first 2 terms, take their ratio, and see what that is. That'll give you the common ratio.
Okay.
All right, so we're going to say our common ratio here is 3 over 2. So we'll say r is equal to 3 over 2.
So plugging in the first like 2 or 3 terms will give me my common ratio of the first term.
Yeah, if you plug in the first few values for n to get maybe, your first 3 terms, right, you can easily see what your first term is right here.
Okay.
And then you can take the ratio of the first 2 terms. So you can do 3 over 2 divided by 1 gives you 3 over 2, right? So that's your common ratio. Okay, so r is 3 over 2. A is equal to 1. Right, so does this geometric series converge or diverge?
Converge.
Okay, what makes you think it converges?
Because we have a actual number there as opposed to like no number or like a...
No, the example I gave here was to tell you that that's not a geometric series.
Okay.
Right. This wasn't about convergence or divergence. This was just not a geometric series at all.
Okay.
So how do we check to see if a geometric series converges or diverges?
Oh, by looking at the sum, right?
No.
Or oh wait, no, that's for like seeing where it converges to.
Mm-hmm.
Okay. Is it the same rules as like the monotonic sequences stuff? Or
No. We're still doing, everything we're doing has to do with just these notes here.
okay. Oh, isn't it with the absolute value being less than 1?
Right.
So the absolute value of R in this case is equal to 1 and not less than 1. So it diverges.
No, it's not equal to 1. Absolute value of R is not equal to 1.
Oh, wait. Wait, are we looking at like I was thinking like we were looking at 1 instead of like 3/2.
Mm,
Okay. All right. So 3/2 in terms of like a decimal from what I think is like 1.5.
right.
So that's greater than 1, which causes the sequence to diverge.
There you go. So we'll say absolute value of R is equal to absolute value of 3/2, which is greater than 1. So divergent. Right. So you don't have to do any more work because this is a divergent series, right? So that's the end of that. Okay. Let's take a look at, see if there's one more example we can do. Well, you know what? That's good enough for geometric series. Let's look at all right. So here we're going to take a look at a few properties for infinite series. Right? So these properties have to do with sums and differences and constant multiples. So just to save time, I'll copy and paste it right from the book. Right, so here's the first list of our properties here. Right, so it's similar to the properties that you have with integrals. Right, so if you have a constant multiple of a sub n and you take its sum, well, then it converges. If it converges, then it converges to c times a. Right, so these are we're making the assumption that these series converge, right? So it says let the summation of a sub n and summation of b sub n be convergent series. Right, so we're assuming that they're convergent. And let a, b, and little c be real numbers if the sum of a sub n is equal to a and sum b sub n is equal to b, then the following series converge to the indicated sums. So the sum of a sub n converges to a, which means if you multiply by a scalar multiple, then your sum is going to converge to the multiple times a, right? Times capital A. So as an example, we know that the sum from n equals 0 to infinity of 1/2, this should converge to 2, right? Because it's geometric, and for geometric series with a common ratio of less than 1, it converges to a over 1 minus r. So if a is 1 and r is 1/2, then this converges to 2. Now, if I multiply this by, say I multiply by 3, right? So suppose now I do sum from n equals 0 to infinity of 3 times 1/2 to the power of n. I forgot to put the power of n here. But 3 times 1/2 to the power of n, this will just come out to be 3 multiplied by 2, which is 6. Right? So if you multiply the indicated a sub n by a constant multiple, then whatever this original sum converges to also gets multiplied by a constant multiple. Okay. Now, rule number 2, since both of these converge, then their sum converges to the sum of their so the sum of the values they converge to, right? So as an example of this, if you have sum from n equals 1, or it doesn't have to start at 1, it could start at wherever you like, but sum from n equals 1 to infinity of a sub n plus b sub n, this can be written as the sum from n equals 1 to infinity of a sub n plus the sum from n equals 1 to infinity of b sub n, which is equal to a plus b. Right? Remember, when you're summing a sub n plus b sub n, you can break that into individual sums. Now, for rule number 3, it's the same idea, but just with a minus sign. All right, now let's move on to another important property here that we use to help us determine divergence. This is called the nth term test for divergence. All right, so what this test says is that if the sum from n is equal to 1 to infinity of a sub n converges, right? So if this sum converges, then the limit as n goes to infinity of a sub n is equal to 0. Okay? So pay very close attention to what this one is saying, because it doesn't mean that just because the limit of a sub n is equal to 0, as n goes to infinity is equal to 0, then that this converges. That's not what it means. Right? So say, for example, I gave you a series, and you took the limit of the sequence, and that gives you 0. Just because the limit of the sequence equals 0 doesn't mean that the series converges, right?
But
But if the
Oh, I was gonna ask if it's vice versa, then it equals 0. Like a sub n equals 0.
yeah, so this is saying is that if the series converges, then the sequence converges as well. Okay. However, we'll say just because the sequence converges, doesn't necessarily mean the series converges. Okay. So what this is saying is that oh, hold on just a second. Yeah, actually this is fine. Let's go up here and then whatever. I'll just write it up here then. So let's continue. We'll say that if the limit as n goes to infinity of a sub n is not equal to 0, then the sum from n equals 1 to infinity of a sub n diverges. Okay. So here we saw that if the series converges, then the limit of the sequence is 0. Right. So if the series converges, the sequence converges.
Mm.
But if the sequence it converges to, or if the limit of the sequence is non-zero, then the series diverges. So let me give you an example. So say, for example, we have the sum of 1 over n from n equals 1 to infinity, right? If we take the limit as n goes to infinity of the sequence of 1 over n, right, So 1 over 1, 1 over 2, 1 over 3. If we take the limit as n goes to infinity, well, we get 0, right?
Mm.
However, the sum from n equals 1 to infinity of 1 over n is divergent. Right, so this sum here is divergent, even though the limit of 1 over n as n goes to infinity is equal to 0. Right, so this is a special kind of series called the harmonic series. Right, and it's an example of this sort of property of series. Okay, so what this means is we can always check for divergence by taking the limit of the sequence to infinity. If that limit is non-zero, then the series diverges.
Okay.
Right, so we can always check for the divergence of a series using the nth term test. Right, so the nth term test says that if the limit as n goes to infinity of a sub n is non-zero, then the sum as n from n equals 1 to infinity of a sub n diverges. Okay, so let me see. We'll stop here for now,
Okay.
and I'll save these notes and upload it to the drive.
So with that definition from earlier, it's in a way saying like if the series converges, it can equal a sub n can equal 0 rather than it being like it will equal 0.
No, it says that if the series converges, then the limit as n goes to infinity of a sub n is 0.
Oh,
If it converges,
okay,
then yeah, it definitely is 0. But
Okay.
just because the limit is 0, if you were to test it out, just because the limit comes out to be 0 doesn't necessarily mean that it's convergent, right?
Okay. All right.
So that means that you can test for the divergence. And the way you do that is by taking the limit of a sub n. If that limit ends up to be 0, then it's inconclusive. The test is not telling you anything. But if that limit ends up to be any other number, then the series diverges.
Okay.
All right, cool. All right, man. So good work today. I'll upload everything onto the drive, and I'll see you on Wednesday.
Cool.
All right.
See ya.
See ya.